and we have this, when teachers teach it as science, and the kids are already seeing everything. So, other schools require it.
Yeah, and that should be good, right? You can't do this, right? Or everybody should do this amount or whatever. Because you can't say apples to apples if we're doing different things.
I know that Adam's glad that you all are here, because there for a minute, we thought it was just gonna be the two of us. We're trying to figure out how we're gonna have a class. But that was early, so we were jumping the gun a bit. But today is our official last meeting day, and we'll go ahead and get started. One of the things that I wanted to talk about is the final. For this last week of class, it's basically the only thing that you're doing. And it's going to be posted on Friday, and it'll be due, this says Wednesday, June 21st. That's because I made that in advance. But if you go down to our module, so tiny. Why is it so tiny? And I left my glasses at home, so I can't see. It'll be posted on Friday, June the 15th, due as an email attachment by Thursday, June 21st at midnight. So as long as you have it in sometime during the day on Thursday, it's fine. If you have to stay up to 2 in the morning on Friday, that's okay too, because I hopefully won't be up yet and I won't know. So just turn it in around Thursday, June 21st. The reason why I'll be a little flexible with that is because your grades don't go on the transcript till the end of summer too anyway. I'll tell you what your grade is in advance, but you won't see it in the IU system. So if there's, for some reason, you can't turn it in until Saturday, that's one of those things. But shoot for Thursday if you can make it, but if you're late, it won't be a big deal. And then just make sure, as usual, that you put final exam in the subject line of the email. I'm gonna try and make this bigger. There we go. That works. Okay. All right, so I am recording now. There's no one else live, so I guess that everyone else in the class will be watching the recording, and then they're going to be doing the attendance summary and posting that. I'll also post a link for anyone else who wants to look at the recording. I don't know why you would, maybe you would. Nothing on Khan Academy, nothing in the discussion forum, and no weekly problem solving. But at the end of class today, we're going to start an expanded problem that will be on the final. So you'll have a chance to start working on that in advance of the final. And use the work that you do here today on your final exam. This past week, when I posted the links to Annenberg instead of Khan Academy for geometry, the reason I did that is because, not because Khan Academy, I think I stated that it wasn't as strong as the other content areas we looked at. That's not really the case. I mean, what they have around geometry is very good, but it's hard to make that alignment directly to the Indiana standards for middle grades math because of the way they have it structured. If you remember, even when we looked at probability statistics, some of those pages were just like laundry lists of everything you can imagine. It's even worse for geometry. So I wanted you to focus more on the geometry knowledge that you need to know for teaching middle grades math, and Annenberg did a better job with that without trying to parse through all those lists. So today we're going to talk a little bit more about geometry in the middle grades, and we're going to end with that question that you'll see on the final and give you a chance to work through it as a team. Middle grades is first of all, how's everybody doing? I just feel like I jumped in there, and do you have any concerns or anything going on? Get started? Enjoying your summer?
Busy.
I know.
Busy all the time.
Yeah, so this past week at BCSC was training week, right?
Yeah, yesterday and today.
Yeah.
At our summer conference, but then, you know, Liam's doing band camp and students camp and this, that, and the other.
He's old enough for band camp and students?
going to sixth grade this year. So, I've been playing Uber for him.
Oh, I bet, yeah. No other news?
How are you?
I'm fine, everything's just typical craziness in my life, but everything's fine. Other people in my family not so fine, but that's okay too. We'll get it taken care of. There's always someone who needs me, you know, at my home or their home or somewhere.
Try being the pastor's wife. I've
Oh,
already been to the
goodness.
hospital and the rehab center and training today.
Yeah, so it might not be that crazy, but it's along those lines. Okay, so I have a particular interest in geometry because when I was a doctoral student at IU Bloomington, my research area was geometry in the middle grades. So this is really near and dear to my heart, and I've read a lot about it. I've worked with kids a lot in middle grades with geometry content. And it's an interesting time because students are starting to think differently in middle grades about geometry. I think, well, my conjecture is that geometry understandings rely so much on a visual that sometimes the visual overpowers what logical thoughts you have about a geometry program or problem, because that visual is there, it's going to influence how you think. So, according to the research, in the middle grades, kids are moving from this inductive way of thinking to more of a deductive way of thinking. So in terms of geometry, they're going from, if you think back, you know, to preschool, to infants, how they work with shapes, you know, get a shape sorter. And they try to put the round and the square, and it doesn't fit, and then they finally figure out the square goes in square, the round goes in round, and it falls into place. So they're kind of testing those understandings. Really has a lot to do with the way things look, you know, and manipulating shape and having experiences with them. And they don't necessarily form formal understandings of properties of shapes until they get much older. And I'm convinced some people never do form those formal understandings, and that's okay. You know, you find ways to function around it, but middle grade students are likely functioning at various stages of reasoning, and it's important to understand which stage of geometric reasoning they're at so you can plan instruction. And I have some very interesting examples of how that works. The researchers who kind of pioneered this line of research were the Van Heelys. It was a husband and wife team. And since then, some other researchers have modified these levels, but they basically have the same underlying principle for each level. But they, for some reason, start with level 0 for the basic level, and that's visualization. So, for instance, if a child or a young adult has developed this visualization line of reasoning, the shape represented by this sheet of paper might be different than the shape represented by this sheet of paper, simply because it's in a different orientation. So everything is visual. It might not be the orientation, it might be that a red piece of paper is different from a blue piece of paper because they're the same color. If you had two different if you had one shape, let's see, I'll hold it now. Both of these are rectangles, we know that. But to a child in the visualization level, the difference would be that one is bigger and one is smaller, and they wouldn't go beyond that. So it's just a very basic visual difference. Then as they move farther down, they start attending to properties. So with the analysis level of understanding, students might notice that in this rectangle, this side is shorter than the shorter side in this rectangle. So they notice a side. Okay. It's still a lot based on visual, but they might pick up on one property. As they move down farther, they notice more and more formal properties of shapes. Things like looking at measures of angles and comparing them, numbers of sides and comparing them. When they get to the level of rigor, they're really able to, it would be something like if I had a collection of shapes, and within the shapes there were rectangles, parallelograms, triangles, pentagons, they would be able to distinguish between classes of shapes by property. So they're kind of doing proof and making conjectures, and they're able to compare those properties across many classes of shape. All right, so these are a few of the things that we have to keep in mind. Students' levels are not affected by their age. So that means that in the research that I did with middle grade students, I had 6 students, and a couple of them were completely influenced by the visual. They weren't even interested in thinking about angles and sizings or anything like that. If a shape appeared to be a certain way, it was in their mind. So you can have middle grade students who have not developed that more sophisticated thinking, and you have to think about how can I go about helping them grow if that's where they're operating at right now. And students don't need to master each developmental level to progress. So it could be that they skip, maybe in 4th grade, you tested them, they were at this visual level of thinking, and by 5th grade, they're able to, apply formal definitions of shape to their problem solving. They don't have to progress through the levels in order. Oh, and levels determined by concepts that have been taught to the students. It's not. So it doesn't necessarily mean that if let's see, how do I say this? If they encounter curriculum that requires them to pay attention to the length of the sides or the measurement of the angles, they might be able to regurgitate that to you and show on paper that they do that, but that doesn't mean that they're operating at that level of thinking. And that's really confusing to realize, but it's possible that with examples and with prompting, that students can appear to know something that they're just being able to apply from what you taught them. It doesn't mean they're naturally thinking in that way. All right, so let's look at, these are a bunch of triangles. And I thought it would be interesting to think about, in this collection of shape, how students operating at these different levels of reasoning would address this collection of shape. Okay? So let's say that I have a student and I believe that the student is operating at a level 0, at visualization level. And I ask them to sort these shapes into piles based on ones that they think are alike. What do you think they would notice or pay attention to?
Maybe the right angles.
Would they call them right angles?
No,
necessarily?
it's just that they have that more of an L to them.
The one at the top right is more of the traditional.
What do you think they would match up? Would they find another shape that they would say would be like that one that would form a group? And why do you think that?
Something that kids in my class, and they would say that that's a triangle, but that's not a triangle.
Yeah, right. So I was thinking, like with this one, I mean, it's bigger, but when you think about if I could rotate that, it would look very much like, I'm guessing that's an isosceles or right angle equilateral triangle, but that would be very much like it. So if you weren't focused on the visual, I could see that one going with it, just a little bit bigger. And the same thing here, right? Those are kind of similar. Yeah, but I think you're right. I don't think they would match any of these together. If a child was able to kind of, in their mind, move things around, these two might. But that orientation is so important. I made a mistake when I did my research because I had some shape learning activities, And on the back side of these cutout shapes, I numbered them. And so the kids are smart, right? So they're playing with it, trying to make these piles, and they turned it over. They were trying to figure out which way the shape goes, which way is up. And so they turned it over and saw the number and said, oh, it goes this way. So they weren't paying attention to the orientation, but they weren't comfortable with thinking about it. It's probably me. My husband's probably looking for my glasses. Sorry, turn them off. Yeah, so any clues like that that they use to try to put it in the correct position means that they aren't comfortable with a shape being in another orientation. That if a triangle doesn't look like the one in the upper right-hand corner, then it's probably not a triangle, it's something else. Okay. What about for level 2, the analysis, or level 1 is what they call it, the second level analysis? What could they attend to and make some groups of shapes from this collection?
They might say like, the one that's on the far left is like spiky, and then there's a couple other ones that look like that. They have a really short base, but they're really tall.
Right, right. So they're trying to find a characteristic of the shape that they could attribute to more than one. Okay, they might even say, well, I'm going to choose this one and this one because it looks like these sides are the same length. Or they might say, I'm going to choose this one and this one because they're about the same height. So they're attending to some characteristic, not just the way they look. Okay, what about level 3 or level 2, the third level? What do you think the next step would be?
Maybe talking about angles.
Yeah, so that's when you get into the formal properties of shape. If they're looking at angles, if they say in particular that it's a right angle, if they say it's a acute angle, an obtuse angle, they're attending to formal properties of shape. Okay. And I have a little cheat sheet here coming up. It shows, so in level 0, the visualization, it's based on visual properties. It could be small, medium, or large, and position is important. Level 1, the analysis is, they group them based on one characteristic like side length or angle size. Level 2, that's when they're starting with the informal deduction. They base them on more than one characteristic, and it's something, usually something formal about them. And then level 3 is when they are in full deductive thinking and they're grouping based on formal definitions. So that's when they would talk about isosceles triangles or right triangles or defined properties. And then level 4 rigor is when you're making connections between geometric systems. So they might say, how a triangle might relate to a parallelogram. They're able to cross those classes of shape. Okay, this is the problem that got me interested in geometry and how kids think about it. Because I was working on a research project in Bloomington where we were analyzing data of the NAEP assessment. You guys looked at some of the NAEP questions a few weeks ago. So we ended up with about just under 1,000 student responses to this question. And this is a 4th grade question. So 4th graders were asked to think about those two shapes and list as many ways as they can that they're alike and as many ways as they can that they're different. What do you think kids would say? 4th grade kids would say about the rectangle and the parallelogram.
Both have 4 sides, 4 angles.
Same height.
Okay, you're all saying properties. What if they were operating at a visual level? See, you aren't operating at visual level because you're talking about the properties. They're not the same, that's right. Visually, they're not the same. Okay, what if a child believes that those two things are not the same and they're asking what ways are they alike? What would they say?
My kids would say that they are not the same, they would stop and wait.
Yeah,
They might have said it looks like
Okay.
they are otherwise leaning,
Okay.
and it looks kind of the same, but it's leaned over.
Right, yeah. So kids who are operating at visual level and they're forced to say why they're alike, they're going to be talking about just the way they look, that it's leaning, that it's tilted, that it's slanted, that's crooked. Well, what I found out is that a lot of kids say that. And so that's why we started the research project. This is what Nate says that they should say. And if you think about those Van Healy levels and where the scoring guide says the kids should be, they both have 4 sides. Okay, so that's a formal property. That's at least a level 1, right? An analysis level. They have parallel sides. Parallel sides, that's a formal definition. We're talking level 3 on that. They have 2 sets of sides that are the same length. That's probably a level 2. They have the same area, level 3. They have the same length, depending on what they mean by that, like level 2 or 3, or 1 or 2. And they have the same height. That could be a level 1 or 2 also. So the kids in 4th grade, they're expecting that they're going to be, right close to the informal deduction thinking in geometry. That doesn't make sense. I don't know how. And one part of me says, how did this item get in the test bank? Okay, this is the way they're supposed to be different. One has 4 equal angles, and the other does not. One has right angles and 4 perpendicular lines, the other one does not. And it says students do not need to make the comparison. They can just say one has 4 equal angles. One is slantier than the other, or one takes up full squares and the other does not, and they have different perimeters. So the only entry in the scoring guide that relates to that lower level of Van Healy is number 3. We'll talk about slantier because that's visual. Now, for the test developers, they probably aren't interested too much in the visualization level because it is a very simplistic way of thinking about shape. But in terms of assessment, when we think about assessment as teachers, we don't want to pose a question that we know half of our students aren't going to be able to answer. So it doesn't make much sense as a teacher, but for the test developers in DC, I'm sure it makes time. As you can imagine, the scores on this one, they were really bad. All right, this is going to be very hard to see. See if I can get in my present mode and make it better. There we go. All right, so here's what the kids said. Over here on the right-hand side are their responses. The one on the right has lines that are slanted. The one has slanted sides, the other doesn't. One has straight sides and one does not, okay? So when you think about that, these are from how the student said that the shapes were different, okay? In that case, they're talking about the attributes. So if we think about their thinking, they are at least looking at a characteristic of the shape. It has to be a level 1, right? Because they're saying the one on the right has lines that are slanted. We interpreted that as being the side. So they're looking at something particular about the shape. The next group, they looked at one shape only. So the first one is not leaning. One is slanted, one is bent, and one tips to the side. And then others would look at both shapes and describe one is skewed and the other is not. One is leaning, the other one is straight. One is slanting, the other one is straight. The one on the right is tilted, the left one is straight. And then some of them compare, they both are squares, but one is tilted. They are shaped alike. The second one is leaning to the right. They are both the same shape, but one is slanted. Now, isn't that interesting? I find it interesting that these students see a parallelogram and a rectangle as being the same shape. And then the last group is when they look at both shapes, they describe one shape as being made into the other. The parallelogram is either made into the rectangle or the rectangle is made into the parallelogram. If you move the crooked one over, it will be the same, because if you slide B over, it can be the same as A. They bent the first one to get the second one. So those kids were kind of, the way I thought about it, when I read those, it's sort of like they see them in their mind, they're kind of moving them to make them the same. This is the coolest set of student work I've ever seen. All right, here's an example in the students writing it, because if you slide B over, it can be the same as A. They didn't name the shape, but they talked about how to move it. And here's some other ones. They just twisted that to that. They're a different shape. One is a parallelogram and one is a rectangle, so that's more formal language. So that's operating with the definitions in mind. And over here, the figure to the left is made up of horizontal and vertical lines, while the other is made up of diagonal and horizontal lines. The figure to the left also has 49-degree angle, and the other has a 90-degree angle. We spent, my co-researchers and I spent the longest time trying to figure out what that meant. The figure to the
I
left
think it
is made
says
up.
490 degree.
Oh, you're right, I'm sorry. Yeah. They said the figure to the left is made. You should have been on our research team.
I can just read the kid writing.
I know. Horizontal and vertical lines, while the other is made up of diagonal and horizontal lines, and the figure to the left also has 4 90-degree, you're right, and the other has 0 90-degree angles. So this kind of response is what the scoring guide anticipated. And these were very, very few and far between in what fourth graders are doing. Okay. I think
They
that's
don't have the vocabulary. I mean, if they haven't been exposed to it, then they won't have correct vocabulary to explain like horizontal and vertical lines.
exactly, yeah. All right, so what, okay. This resource that I've given you a link to is really nice. It's a blog, or whatever they call them these days. But what's really nice about it is they've gone through with each level. Let me find it down here somewhere. Oh, they have each level provided. They give you a little synopsis of what that level means. But what's really nice is they tell you if you're working with older students and you find that those students are still operating at that visualization level, here are some things you can do to help them grow in their thinking. So they're saying, the example is the shape is a rectangle because it looks like a box. So that student's not attending to any of the formal properties of the shape, just the way it looks. So they say practice transformations to see the shapes are congruent when turned, etc. Use geometry software to explore triangles, parallel and perpendicular lines, angles, quadrilaterals, and circles. When students can drag vertices and display measures, they can really begin to grasp how the properties of each figure work. Did any of you download the Geometry Sketchpad or have used that before? There's a free education version. You can't print or save from it, but you can get into the software and use it. And it's really nice because you can take a shape and flip it all different ways and measure different properties of the shapes. That's a really good way for them to interact with the shapes. I don't know if they give us links to the, but they have it for each of the levels. So I wanted to look at, for level 2. So they're saying that the thought process is that the figure has 2 pairs of congruent sides, so it could be a rectangle or maybe a parallelogram. But there are no right angles and opposite pairs of angles are congruent, so it must be a parallelogram. So what happens if the students are stuck at that level?
Which shape are they talking about?
Oh, let's see, it's up here.
Because none of that looks.
Well, it's a rectangle. They're talking about a rectangle and parallelogram. Students may have trouble, they don't give you the. Student can draw conclusions in the order. These. The figure has two pairs of congruent sides, so it could be a rectangle or maybe a parallelogram, but there are no right angles and not pairs of angles are congruent, so it must be a parallelogram. Okay. Well, they're talking about a rectangle and a parallelogram, but what they show us doesn't tell a
So I think what they're showing us are just alternative activities for level 2. These is activities for level 2, and that's what those pictures are.
Yeah, right. But they don't give us the original question that they were asked. I don't know why. Okay. All right, so they're giving you, what I found interesting was the card sort. What I've used in the past are Venn diagrams where you try to find common properties of shape, and with the Venn diagrams, the common properties come in the overlapping part. But you can do card sorts as well, where you're attending to multiple properties, because that's the difficulty for kids. You know, they might notice the angles, they might notice the side links, but to make sure that they're attending to multiple properties at the same time is the issue. So I thought this was a good resource. There are a lot of good ideas in here. Yeah, this is the problem. There's not a lot, you know, for the highest level, because most students don't even get to it. Even in college, I would argue that they don't. It says the grasp of geometry has been extended to a level of a mathematician. The student has an understanding of non-Euclidean geometry and is able to compare the study of geometry to other areas. This is so funny. So when I said that my dissertation research was in geometry, so I'm in my presentation. After you get through all of your formal coursework, then you take as much time as you need to do your dissertation, and then when it's finished, you get your committee together and you go into a room. For those of you who are here, sort of like that block 1 thing that you had to come and tell professors. Yeah, remember that? It's like that. And so you go into the room and you choose your committee based on, you know, the faculty expertise, and you can provide the most feedback, helpful feedback to you. So I knew that 2 people on my committee didn't see eye to eye about the methods that I used in my study. They had different ideas, so I knew it was going to be interesting. But I get in and I do my presentation, and I was relieved for a while because the 2 of them started arguing back and forth with each other. So it took all the pressure off me. I just sat there and listened. But then the older one of the 2 decided that I needed to answer questions about beach ball geometry. I've never heard of beach ball geometry. Has anyone heard? There's a geometry that's based on the surface of a ball. And he was trying to get me to answer questions about it. Now, he, based on the questions he asked me, was beyond the level of rigor. He was able to connect, you know, Euclidean to non-Euclidean geometry to beach ball geometry. And I have no idea what he was talking about. But that's what they're really mentioning here with rigor. It's understanding concepts in such a way that they, you know, cross other systems. The closest that our students will get to that would be, you know, 2-dimensional and 3-dimensional shape, shapes within the 2-dimensional world, like comparing classes of shape like trapezoids and hexagons, I don't know. But for the most part, no one that will encounter in K through 12 will reach that stage. I am interested in beach ball geometry now, though. I've just never taken it up. Beach ball geometry. All right. That leads us to our work. I have, all right, so we're thinking about, part of this is thinking about how you go about understanding shape, because I'm asking you to think about area, which you already know. I know you know there are formulas for area, so kind of forget that for a little bit. if you can. And we want to be able to create and explain a model to determine the area of one shape based on what we know about the area of another. Okay. So the first, I'm going to give you some, because I think it'll be easier if you have red paper that you can draw on. And I'll get you started and just kind of turn you loose, see what you come up with. I have scissors too, so if any of you want to draw and cut in a little while after we get you started, that's fine. All right, so you're gonna, first off, start out with a rectangle, and I want you to be able to develop the area of a parallelogram from the area of a rectangle. Okay, so the best thing to do to start out with is think about what you know regarding the area of a rectangle. You can draw it, you can write something symbolically. I think the visual model will be your best bet at this point. And then think about what you would need to do to transform that rectangle into a parallelogram, and how you can use what you know about the area of the rectangle to determine the area of the parallelogram. Okay, you want me to do something on the board to get started? Okay, this activity really represents a conceptual way to introduce area, okay? So if I have a rectangle, one of the things that's really difficult, or actually it's sort of a misconception, if we're talking about area and we want to model it, we usually use some sort of manipulatives and kind of cover something with unit tiles, but those unit tiles themselves aren't two-dimensional. They have 3 dimensions to them, length, width, and height. But area has only two dimensions. So we're thinking about something that has no depth to it at all. And that's confusing when we use tiling activities. But with area, it's about covering, we know that. So with a rectangle, I could just cover it with tiles and count up the number of tiles and I have the area. No problem. But with a parallelogram, what happens?
Cut up.
Yeah, you have to either cut up the tile or something, because you have those non-right angles here, and you're not going to be able to fit the whole tiles on there. So how can I take, I mean, even if you don't know the area formula for rectangle, you could count up the squares and find the area. But how could I use that knowledge to determine the area of a parallelogram?
By matching the parts that are cut up to each other to make full blocks.
Okay. So that's what you're going to have to build a model of. How can I model that to show that I can create a parallelogram that has the same area as that rectangle? I have a few up here. Okay. So let me go ahead and say a little bit more about the other 2 parts, because some of you might finish one part and go on. So for the second one, you want an area of a triangle from the area of a parallelogram. So starting with the parallelogram, how can you create a model for the area of a triangle? And then finally, the area of a trapezoid from the area of a parallelogram. anyway, and we can talk while you're doing this if you have questions or thoughts as you're working, or do you want to share and work with something? Yes. You can do that, or you could do.
Right, no, I know, I just mean like, if you're trying to show conceptually how,
Yes. Oh,
I mean, like, I'm used to doing it that way, I'm just saying, like, match up the blocks.
Yeah, that's
for
great.
the same area,
Mhm.
show improvements.
Right. Okay, so what you want to show is that you could think of it as, how can I show that I could have a rectangle and a parallelogram with the same area? How does it relate? So, yeah, exactly.
Right.
Yeah.
So I was just like,
No, that's it.
missing.
No. Pretty much it. Yeah. So you might want to just maybe leave that there and draw your parallelogram and show how. Yeah. That's perfect.
Making sure.
No, you're right. Any other questions?
It's like these two go together.
Uh-huh.
Yeah, so it's making 36.
Yeah, so what you end up with, where does this and this come from? Where did the dimension come
So I know that it's 4 up, so the side's like 4 here. And I know going, this is going 8, but when I put these two together, then that's my 9.
from? Not in my story.
Yeah, no,
It's like I'm the.
This is what it was when I was asking me, almost 2 hours to get here, because it's 465. Really? But it's down to 15 miles an hour, that's what it was doing. I thought I was gonna be late getting here. And then you stopped until like, everything's gonna be
Oh.
let's go.
And they've done that before, when we've been in White Soil.
Yeah.
So, and some of them runs.
Mhm.
No.
Yeah. That's right. Mhm. Now, why did we do that? Well, where's the 4 name? Yes. Mhm. Yeah. Yeah, so you just might want to work either label that or like show how those two are related.